So what's an intertidal zone along the coast? So you know there's tides, right? So at high tide, the water levels are high, low tides are down low, and if you've got a rocky coastline or boulders along there, or maybe even just a jetty that was built to go out, like you see at Barnegat Inlet and other places, some of that will be underwater during high tide and will be exposed during low tide. And if there are, it's facing, especially facing the ocean, it probably has wave action on it. And so there's going to be periodic wave action in that intertidal zone. And so they were looking at barnacles. How can different species of barnacles compete for space on the rocks? So a barnacle is, what's a barnacle? They're actually crustaceans. So it's a little arthropod, and they attach themselves to the rocks. And they kind of close up. It looks like a shell. So if you're collecting shells on the shore, and you might see some blue mussels, maybe some oysters, and other kinds of shells attached to the rock. And then you see something that's like, I'm not sure what kind of shell that is. It looks almost like it's got, they're not the same kind of shells, almost like a giant tree bud or something. Well, when they're underwater, in the high tide, that'll open up, and there'll be sort of a crayfish-like creature with that has appendages that almost like fan-like, and they're catching really, really tiny stuff to feed on. And so their life cycle is, in order to reproduce, they're sessile. That means they live attached to something. Permanently attached to a rock. And then they reproduce. The eggs go out into the water. Huge numbers of eggs. Very, very are selected. And those eggs and then the larvae that hatch from them are what you would call plankton. That's this stuff, this living stuff that's in water. To complete their life cycle, when they get old enough, they need to come back to a rock and be able to attach to that rock. If they don't, they can't reproduce. They'll die. Basically, they'll get eaten. The bigger they are, the more vulnerable they are to being eaten. And so that's their life cycle. So what we've set up is, here's how this works. So we have 3 variables. So E is disturbance, and it's a rate, and it'll be number of individuals per unit space per some time. So disturbance, and think of it, how many would-be barnacles who are trying to attach themselves to the rock get knocked off the rock per square meter of rock per day. So that's a rate. There's also a colonization rate, C. And that's also number of individuals per unit space per time. That's the rate at which each species can colonize the rock. So here's the rate at which they get torn off the rock. Here's the rate at which they can attach themselves to the rock. And the only other thing is competitive dominance. And that is which species are able to displace which other species from the rock. So let's set up a table, and we'll say we'll have 3 species, A, we'll have A, B, and C. And we'll say the colonization rate, what shall we make? We'll say, is 3, 6, and 9. In other words, species A, barnacle species A, on average can have 3 individuals attached per square meter of rock surface in the intertidal zone where the waves are hitting it per day. And so it's got a low colonization rate. C has a higher colonization rate. And here's our dominance. Is, we'll say I, meaning it's a good competitor, and we'll make B in the middle, and we'll make C the lowest. What does that mean? So we could actually, if we wanted, and their full model does this, we can give different values to this and say that A has a 80% chance of displacing a B and a 100% chance of displacing C, and C has a 90% chance of being displaced by, and you can do all those. Let's just make it real simple just to illustrate the concept. A always, so A can always attach itself to the rock. Listen to that. If there's a B there, if it's coming off the rock, it's that place. And if A encounters a C, it can kick C. B will always lose to A. So B can be on the rock unless an A kicks it off. But if the C comes, B can kick the C off. Or if B arrives and there's a C already in the spot, it can kick C off. C can only inhabit a spot where either A or B already is. And if an A or B shows up, it'll get kicked off. Does that make sense? So real simple. Complete total dominance. Now, you'll notice the only rule here is that the colonization rates have to be ranked exactly opposite. Does that make sense? If you are a really good competitor, are you going to have a small clutch size or a large clutch size? Well, let me put it this way. If you are a very poor competitor, what's your strategy? As many as you possibly can, right? So, and so A's are good competitors. So they don't need to have as high colonization. So that really does make sense. Okay, so let's do this. On those rocks, right? And so,
what is this?
So that's our disturbance. So that's our uppercase epsilon, the Greek letter E, a capital E, epsilon, and it stands for disturbance. Now, let's consider each of these 3 species one at a time, and consider them in the absence of competition. So if there was no competition and species A was all by itself, in the absence of competition of disturbance, what would the population density of A be? And to what? Yes. To what point?
To its first complete dominance?
Yeah, and so what population density is that can be sustained indefinitely, given the resources? Yes, I heard it, carrying capacity, awesome. So, I'm gonna put in K, and here's K sub I, meaning I'll have the carrying capacity of all 3 species, I'm just gonna rank them, I'm gonna scale them to the same, so that it makes sense, right? So in the absence of competition, and the absence of disturbance, we would expect species A density, population density to be at carrying capacity. As this increases, as disturbance increases, what should happen? It should be less, lower and lower. Is there a disturbance beyond which A can't exist? Yeah, and what is it?
A hurricane?
Well, exactly what is it? In terms of species, individuals per unit space per unit time. Yes, why 3? right, so when the chance of being torn off the rock equals or exceeds the chance of attaching to the rock, that's too much disturbance. Exactly right. So we can draw a straight line from here to here to show species A.
Why is it doing three exactly?
Because its colonization rate is 3. That 3 is the problem, A has a probability on average of attaching 3 offspring, 3 young to the rock, per space-time. But the probability of being torn off the rock is 3. So when the probability of being torn off the rock equals or exceeds the colonization rate, they can't exist there. The disturbance is too harsh for them. Does that make sense? So what about competition? Is A under the threat of competition?
No.
No. So this is what we really see for A. Question?
So this is disturbance on the X. right?
Yes, the x-axis
So,
is
and
disturbance.
you said 0 was.
No disturbance.
No disturbance, and 10 was like waves are crashing on the
Yeah.
rocks, right?
Uh-huh. So from calm to really rough.
So, now, but it's the probability that they would survive, so it's 3,
So all we're looking at is attaching the rock or being torn from the rock. And survival depends on that. If they can attach to the rock, they will survive and reproduce. If they can't attach to the rock or get torn off the rock, they're back in the water, they're plankton, they're gonna get eaten. Yes,
So because A is dominant, the I says no threat of competition.
there is no competition. Exactly right. So now let's do the same thing with B. In the absence, and I'm gonna use I'm gonna dot this. So don't make a hard line, but I wanna put in a reference line first and then we'll fix it. In the absence of competition, what would be B's relationship with disturbance? In the absence of disturbance, B should be how high? To its carrying capacity. This high. And, as in areas with greater disturbance, or in the same place if disturbance increases, what would the relationship be with population density? Is there a disturbance level beyond which B can't exist? Yes, and it's 6. Now here's where I'm gonna draw a reference line, so be careful there. That's what B would do in the absence of competition. Is there any range of disturbance between 0 and 6 where it really is free from competition? Yeah, from 3 on. From 3 to 6, so let's make that a solid line. Because it really is absent from competition.
How do you know where to make a solid line?
Hmm?
How did you know where to make a solid line?
I drew a straight line, K, from at 0 at K, I'm sorry, from K at 0, disturbance, to N equals 0 at disturbance of 6. That was a straight line. And now I'm just filling in that line from 3 to 6 because it is in the absence of competition. Okay? Yes?
So the darker line is in the absence of competition.
Yes, because A can't exist beyond 3. So it really is free from competition. Now, if we get to the small, light, lower and lower levels of disturbance, what's gonna happen? It's gonna suffer from disturbance, or sorry, from competition from A. And in fact, it gets worse and worse and worse as the disturbance gets less and less and less. So we have to bend this line down. I'm gonna bend it down in a particular way because we're only using 3 species. If we use like 12 species, I would do it all random, but I'm gonna cook it a little bit just to demonstrate how this works. If this line goes straight down, that means that the first molecule of an A drove the entire B population to local extinction. That's not realistic. So it shouldn't go straight down, it should come out something like this. If it doesn't bend enough, it's gotta somehow hit zero, otherwise A will be competitively excluded, which we know it will. So a good place to do that, let's put it right here. Like that. So there's one. All right, and so really anything from about here to here would be reasonable. And it just depends on what those, the competition coefficients would be. We're not. Does that make sense though? It can't,
Why would this start on Zoom?
I arbitrarily made it a 2. I could have drawn it to 1 or to 2, either of those would be reasonable.
But here was
Not really, because that means that A is so inefficient as a competitor, it's not until it has its entire maximum possible density that it could drive someone else to extinction. And we know that that doesn't really happen, because when the two paramecium were growing together, they were affecting each other long before they reached their peak. Does that make sense?
I thought it was more like zero means nothing is logically, so I understood.
So there's 2 zeros here. Here's a 0, and population density is 0. Okay, so density is ranging from 0 to K. Disturbance is ranging from 0 to infinity. Yeah.
So the solid line going back means, it pretty much means that because A's competition isn't completely absolute, that it can still grow somewhat.
From where?
Before
Between 2 and 3?
Before 2 and 3 can still grow somewhat.
No, it's out.
Oh.
Because this is hitting 0, so between 2 and 3, by the time you get to 2, there are enough A's around to competitively exclude B.
Okay.
Right? Right here, there aren't enough of them to do that. But this is the threshold density of A to be able to completely eliminate B. And I could have put it here, but I didn't. All right? So one last one. C. In the absence of competition and the absence of disturbance, what would you expect the population density of C to be? N of C would equal, okay. Is there a disturbance so severe that C can't exist at that level or at higher levels? Yeah, at 9, so with the disturbance, the probability of each one off the rock equals or exceeds colonization, the probability of attaching to the rock. That's too harsh of a disturbance for them to exist there. So I'll draw a reference line to 9. Okay, so
So from 6 to 9.
from 6 to 9, tell me about that. What's the situation for, there's no competition? And so what has to happen? Well, anywhere along in here would be reasonable, but I'm gonna push the book a little bit, just to, because there's only 3 species. And draw that. So this is a plausible way that this could turn out. It starts going down because of B, but B is not that great a competitor. It's definitely causing this to come down, but A's even better, and it can't exist very long today. So don't worry about exactly those angles, just that it can't go straight down, and it can't be so wide that it wouldn't hit 0. Does that make sense? So they have to be able to competitively exclude each other. All right, so one last thing to do. Let's draw another graph below it. Same x-axis. And let's keep track of species richness. What's richness? number of species, and that ranges from what to what in this community?
1 to 3.
1 to 3. So here's 0, 1, 2, 3. And let's keep track. So from 0 to 1, how many species are present? Well, there's only 3 species, A, B, and C. How many of those are present? From 0 to 1.
1 is present.
And who isn't?
A.
It's A. Right? Only A, that curve for A, that's the only curve above the 0 to 1. Right? That's the only one there. Between 1 and 2, how many curves will I see? A and C. Very good. And I'll just name them. The order here doesn't matter. And between 2 and 3, how many species are present?
All of them.
They all are, all 3. What's the next range that has the same number of species present, the same richness? From 3 to 6, exactly right. And who's there? B and C. And what's the next range that has the same richness? Don't forget here, 6 to 9. And who's that? Just C. There we go. We're done. So, you want to talk about this first? So what's happened? Do you find the greatest number of species at the highest level of disturbance, the lowest level of disturbance, or something else?
Yeah, something else.
And what might you call that something else? Intermediate, right? It's an intermediate. So, why do you not get the greatest amount of richness at the lowest levels? You're about 1 word for your answer. Yes. Yes. Does everyone see that? Competition. You don't get the highest species richness at the lowest because of competition. Why don't you get them? There's very little competition at high levels of disturbance. How come you don't get the greatest species richness at the highest levels of disturbance?
Is highest level of disturbance.
It's the disturbance, right? It's too harsh
Yeah.
for all the species. So the highest level, the highest richness is found very specifically here. Make sure you can read this. Where do you find at what specific range? Yes, 2 to 3 or 3 to 2 if you read from right to left. Yes. And so if you're asked this, and there's a good chance in the very near future, just assume that the picture is drawn accurately, and so don't say, well, that's like 2.9, this or that. It's like, they're simple. It's meant to be 2, 3, whatever. So I'll give you different ones for that, but to be able to read that. And so that's the perfect answer, 2 to 3. What level of disturbance has the lowest richness?
10, 12.
You got it.
9 to 12.
No,
That's
9,
funny.
9.
Thanks for thinking outside the box. The lowest level is 9 to infinity. And
Oh,
richness
okay.
would be what? 0. So I wouldn't ask that because that's kind of a trick question. So, because most people would say, well, it's not richness if there isn't anything there. But where do you find richness of 1? 6 to 9 and 0 to 1. Perfect. You guys have it. Okay. Last question. I'm seeing R and K selection all over this. Who's the relatively K selected species? A, for sure. Which species has the highest M sub 0? Remember?
C.
Yeah. It's putting this all together. Awesome. And we've already been talking about competitive exclusion, right? That's what's going on here. And disturbance, periodic disturbance. All of these things we've been talking about. They're all kind of wrapped up here. So what's the probability that that will be on Monday's exam? Real high, because it's a really great model. So we've got about half an hour, so I'll open it up to anything you want to talk about. Talking about, what model are we working on? Community, and which one? Which measurement is this? Just put it right on the board. What are we talking about here? Where did you take log? Which community measurement involves logs? Which one? We have diversity. So it's Shannon-Weiner diversity, which is H prime equals, very good, negative, actually that's an S. It's a Greek capital S sigma. Looks like an E in English. It does, yeah, if you kind of pinch this down, you're gonna make it between two, but it's a sigma. And next is P sub I, so it's not pi. Pi is 3.14. Always, don't call it pi because you're getting confused. P sub I. Sub I meaning you've got multiple species and you'll have a P for each one. Just like N sub I, there's multiple samples and you'll have one for each of the species. So it's P sub I times the log of P sub I. All right? So how do I calculate P sub I from this?
I don't know.
What's the total?
200.
See that? 20 and 80, 40 and 60? So 200. Okay, now it's a piece of cake, right? So what's this? 20 out of 200 is 0.10, right? Or the other way you can do it, if this is 200, just divide it by 2 and then move the decimal place. Whatever happens, right? How about this? This would be 0.2, that 0.3, and 0.4. That equals 1.3. Okay, now if I had to get the log of P sub I, saying what's the log of 0.1? Well, it would be this value. So here's just a number, an x, you know, a generic number that you use in any mathematical equation. If it's some x, some value. You can call it anything you want. You call it C, doesn't matter. X is typically means some secret number. And so if this is x, this would be the log of x. And look at this. Right here, what would this be? It would be this times this equals that. So if you had to do this, you could actually skip this step if you wanted to, because you've already got this. How about that? See what I'm saying? Okay, well, so don't worry about it. So the log of x, this, I'll give you this number, right? I'll give you this number. And so you can do that. If there's a 0.3, there would be a 0.3 here, and there would be a 0.4 here. So I will make sure that the number, whatever number you get on P sub I, that will be in the list. And they will be simple numbers like this.
Well, usually,
Oh. Oh, okay.
so the log you usually.
It always, I go slower when I rush. It always takes me longer when I rush. Yes?
But they'll all be written where you can get the missing value usually.
So
Yeah.
there'll be, if I do this, it will be at the bottom of the last page, right there for you to see. The table will be set up. Now, the only thing is, if I put it at the bottom of the page, there might be, this might be a row, and I might have, what, 11 other rows, or no, 20 other rows. I might break that table up and actually put it in 2 parts, just to save space. But you might see this twice, like from here to 0.5 and then 0.55 to 0.1. Does that make sense? So you'll see it. It'll be a table in 2 parts.
And it'll be easy enough for you to be able to get the value of it.
Oh, yeah.
If one was provided.
It'll be real obvious because you'll have these numbers. Every one of these numbers will be in this list, and all you have to do is say, well, where's it?
Okay.
And as I was saying, I'll also provide this for you, which corresponds to that. Then what do? You add them up, and then change the sign, because it'll be negative, make it positive. Yes. Did I answer your question? Yes. Pray that one population affects the rate of the other. And we showed that in a series of graphs, how with prey density on the x-axis and predator growth rate on the y-axis. In fact, let's just do that real fast to make sure we're all on the same page. So predator density, or sorry, prey density, remember, it's a label, right? And this will be time. So this is the predator growth rate, which can be positive or negative. When prey density is really low, should the growth rate be positive or negative? Negative. When the prey density is high, what does that look like? No. On the other hand, if this is predator density and prey growth rate, what should that look like?
Straight line down.
Down. Okay. Now, what we're doing here, we're just going to show the densities. Both of these are densities. So here's prey, and here's predator. So how are we going to show growth rate? With an arrow, right? So an arrow, what kind of arrows can we use to show prey growth rate, the change in prey? Either left or right. How will we show increasing prey?
Right.
To the right. Decreasing prey.
Left.
To the left. And this, so these are predators. How would we show a change in predator density? If they increase, that's,
Up.
and if it decrease, that's
Down.
perfect. And then, to make it simple, this is low prey density and high prey density. This is low predator density and high predator density. Okay, let's start here today. Tell me about how the two arrows should go. How about the horizontal arrow, which is, horizontal arrow measures what? A change in
Right.
prey, so should it be to the left or right?
Right.
To the right, how come? Because it's low predator density, so they should be increasing. What about the vertical arrow? Which way should that go? Why? Because prey density is low, therefore the predator density should increase. Exactly right. Add those two together. Come together. Now tell me, for my horizontal arrow measures what? Right. To the right, because the prey are increasing. Why are they increasing?
Because the predator is low.
Because the predator is low. What about the vertical arrow? That measures what? Predator, and the arrow is the magnitude of the change. And so up, down, which means increasing. Why are they increasing? Exactly. That brings us to here. Vertical arrow, let's switch it up. Vertical should be up or down? Up. Why? Prey density is high, therefore predators should be high.
Going down. Like the predator. What's the prey density?
It's not that the prey, that's not that the prey is high, therefore the predators should increase. It's always the density affecting the rate of the other. And so we're drawing arrows, which is the rate, right? So, because prey density is high, predators should be increasing. Increase is up or down? Up because it's on which axis? The what? Exactly. And what's happening, what does the horizontal arrows tell us about?
Prey,
Prey, and which way should that arrow go?
to the left.
Which is
Low.
low,
Decreasing.
but decreasing. And
Growth.
why is it decreasing?
Because it's not gonna
Because
go.
predator density is high. That brings us to here. Tell me about the horizontal.
Horizontal.
Horizontal measures
Prey density.
prey density. Prey density should be changing how? Decreasing, and that's to the left or right? To the left. Why are they decreasing?
Because the predator is high.
Exactly. Okay, tell me about the vertical, the y-axis. What's going on the y-axis?
Predator
That's the
density.
predator density. Which way should it be going?
Down.
Down, which would be down.
Decreasing.
Decreasing is down on the y-axis. And why is it going down?
Because there's no more prey.
Because
Prey's
predator
going up.
density is low. That brings us to here. Now tell me about these arrows. This never ends. Did you ever hear when you were really little, Sherry Lewis, she had a thing with lamb chop that was like a puppet or something, a children's show, long ago. Well, there's a song this is the song that never ends.
Got it.
And it goes back and it starts over. It goes
It's like a-
round and round and round. There is no end to it. But that's what this is. There is no end.
Wow.
Why?
Well,
Why is it a loop?
because I got back to here and it's, well, it's the predator-prey cycle. It's the predator-prey cycle. It's a cycle. Cycle means what?
It's never ending.
It's never ending. It's a circle. Where's the beginning of a circle?
There is not one.
I had a student argue, well, it's at the top. So I took the page and did this. Now where is it? Well, it's like, no. And so we had this kind of, whatever, exploration all the time, and say, humans tell stories. Stories have a beginning, a middle, and an end. Once upon a time, things happened and they lived happily ever after. That's how people tell stories. But the reality is, things don't always have a beginning and an end. Yes?
Can we talk about the functional responses that should?
It doesn't have any meaning unless you know what the variables are. So what are those variables?
Prey density.
Prey density. So you can think of abundance or something like that, or probability of encounter or something like that, or just straight up N. And this is some sort of measure of amount of prey taken.
It would be acceptable to write that as a label.
Sure. And there's different ways to measure that. It could be,
What do you mean by amount of predator?
it could be the percentage of a certain prey item in the predator's diet.
What is this like when we talk about how the rabbits are so?
That's the predator-prey cycle with rabbits and the hare, with the pelts. And that was being used as a way to sample the population density. It's kind of crude, but even with that crude kind of measure, you can still see the cycle pretty well. So this might be, how about, let's use, in this case, percent of predators diet. So, let's say there's a predator who eats two kinds of prey. Prey A and prey B. And so this might be, this could be, this is prey A. What percent of A is of its diet? And so it could range from 0 to 100%. Okay, good. So as prey density increases, the simplest way to respond to that if you're eating the same percentage of prey, like 50% of your diet, well, actually, no, what that would change. If you eat, when prey is really, really low, it's probably going to be a small percentage. In fact, when prey is zero, they're not eating it, right? And so the more abundant they get, the greater percentage they're gonna eat. So whatever that is. And without knowing these units, we can't really say exactly. You just know it because the simplest thing is the response. And this is a type 1 functional response. Not to be confused with a type 1, what would that be? LX over X. What's LX? Survivorship, right? So that's a survivorship curve. That's population level stuff. So we're doing community. Here's a type 1 functional response. What is unrealistic about this at extremely high prey densities?
Can't eat all.
You can't eat them all. Or what happens if this is 100%? If we change our scale, what if we did something like this? From 0 to 100, and it got up to here. What would happen? It has to be more than 100%, right? Right? That means they're eating them prey exclusively, that particular thing, right? So in any case, let's draw that, what I just did, except do it down here, where for whatever reason, you've saturated the system, either because they can't eat anymore, or that's all they're eating, if we're measuring it as a percentage. So it just depends on how you measure them out. But in any case, you can saturate the system, and that would be what? Type 2. Okay, and then type 3 is where prey are ignored or somehow eaten below their availability when they're rare. And then you have the same proportional kind of increase in predation, and then you can saturate it. That's a type 3. I gave you 2 possible reasons why this might happen. Specific searching image, meaning that they're not looking for it. And so when it's rare, it's not on their list of things to look for because they're not familiar. And refugia, there may be hiding places. And you can probably think of other things. Those are the 2 that are usually come to mind. Got 1 more minute. 1 more minute. Is a probability that a larva can attach itself to the rock. If it does that, it will survive, reproduce, and multiply. If it doesn't attach to the rock, it'll die. It'll become a plankton and will be eaten. And so we've got different rates, and they rank the opposite of competitive ability, which makes sense because if you're really rotten, if you get pushed around by everybody, you better compensate by having lots. If you're competitively dominant, relatively case like it, you are less affected by competition. And so you could invest more. These are probably bigger young, a smaller number of bigger young. Maybe that's why they're so competitively superior. Maybe they're just bigger. So, this might be 100 1 gram or 1 microgram offspring, and this might be 1,000 1/10 of a microgram offspring. And so think of it
So
that
A
way.
is bigger and C is smaller.
It could be. That's the simplest way to do that. And that would make sense both with their colonization rate and their dominance. That's the simplest way for that to happen. In any case, we've got K on this end, R on this end. Okay? And so when you put these 3 together, this straight line is saying, in the absence of disturbance, we expect the population density of A to be all the way up to its carrying density. In areas where there's higher disturbance, there will be fewer and fewer of them. And they can't exist at 3 or higher, because the probability of being torn off from the rock, which is what E is, disturbance, is equal to the probability of attaching to the rock. So it's too harsh. And so the simplest solution is a straight line. That's what happens if there's no competitive interaction, negative competitive interaction, no harm coming from B or C. And we've set it up to make this complete, to simplify this, again, because there's only 3 species, so we've got to push it in the direction. B has exactly the same relationship. In the absence of A, which is the only competitor that can affect B, in the absence of disturbance and the absence of A, B would rise up to whatever its carrying capacity is. We put them all in the same place to be able to drive on spectrum. So we scale it to their respective carrying capacity. And so you get that line. But, so from 3 to 6, it really is free from competition. So that's why I drew that in. However, instead of continuing up this way, as the, from 3 on, 3 or less, it's dealing with greater and greater competition from A, such that by the time there is this level of A's, when A's a little less about like do a straight line with you exactly a third of its carrying capacity, that's enough, dense enough A population to drive B to competitive exclusion. So A's pretty good.
Oh, so competitive exclusion,
Yes, that's what's happening. This downward slope, you're watching competitive exclusion in action. The more A's there are, the fewer B's there are. And finally, when the density of A reaches this threshold, that's enough to drive B completely to local extinction. And then the same thing with C. C, we draw the same line from its carrying capacity to the disturbance rate that equals its colonization rate. And from 6 on, it's free from competition. Now, we have these, like, in the whole model, you can actually put in coefficients and say how exactly what effect this has based on its density, and that would be the linear line for it. And so you can do that. And sometimes, if you've only got 3 species, you might have 2 that will be close to each other. Since we're only doing 3 species, it's really simple. I pushed it a little bit, but that's not unreasonable. That's kind of that's the average of what you would see.
Would we have to drop both of these?
So, someone asked me that earlier today. If I were to have you graph that out, I would still be grading this into August. That would be very, very hard to grade. So, I'll just leave it at that.
So we're not dropping.
You have to understand it.
Okay, just like you want. Well, how is it that way? Why is it so round?
Why is A so?
Like, why is it